the Gaia uh, project really inspired around a long series of amazing ground-based spectroscopic surveys. I think so one of the earliest of these was RAVE, and then I'm afraid I've forgotten to write down LeMost, and we had the SDSS Apogee, the Apogee effort that I'll talk about extensively. And going forward, we're going to have Weave. Weave is just getting going now, getting under steam now, and Foremost will be, I think, happening fairly soon. So we have ground-based surveys taking relatively high-resolution spectra of some of uh, the stars for which we have this amazing kinematic information coming out of Gaia. And in 2014, another very important thing happened for our field, which is that the Kepler satellite suffered some kind of failure, which meant that it couldn't continue with its original program and moved to the K2 program, under which it settled down to simply monitoring the brightnesses of a number uh, of giant stars with exquisite precision. And people have discovered that from these time series, it is possible to extract the masses and thus the ages of giant stars, so that we have information now about the ages of quite distant stars. And I think that's quite a revolutionary development for our field.
James,
So
you already share the first screen, so it's better to share the first screen. Yeah.
I'm sorry, I haven't understood. What, can you not hear me?
No, look, we can hear you, but it's not the full screen. Yeah,
You're not seeing,
we can see your next slide.
you can see my next slide. Oh, you can see
Yeah,
the wrong window. Right.
yeah,
Okay. Well,
yeah,
okay. Let me see if I can fix that. To do that, I need to do this, I suppose.
yeah.
And then I need to share, I need to stop sharing.
It's just now it's
And,
okay, but it's just
and
not.
then I need to share a different screen. Yes, knowing which screen you're supposed to share is screen two. Okay, I think that's probably physically screen. Uh, and then I need to maximize this. Shall we try that?
Haven't tried. Yeah. Oh, it's
Does
okay.
that fix
It's
that
okay.
fix
It's
that
okay.
fixes the problem? Yeah, sorry.
Let's go.
Oh, yeah. Right. Anyway, so what do we need to do? What's our task that we need to deal with? We have to extract from these amazing data obtained at enormous expense um, how galaxies are structured, and we want to know. So that's a very, I mean, that is an absolutely mechanical, straightforward. It must be possible to do it from to extract from these data how galaxies are structured. What's then highly desirable, what we very much want to do and probably can do, is infer how they arrived at these structures. And by structure, what does structure mean? It means how is the dark matter and the stars ordered by age and chemistry are distributed in phase space, i.e. in x and v or some other coordinates for six-dimensional phase space. That's what the structure of a galaxy is. That's what we need to deduce from the data. And I feel very strongly that discussion of galaxy histories is absolutely pointless until this structure has been clearly established. And for our own galaxy, I maintain this has not been established to this time. We are still seriously ignorant as to what the structure, that is to say, the distribution both of dark matter and of stars ordered by age and chemistry is, what the distribution is of these objects in phase space. And the reason to some extent is that this structure is buried in the data by selection effects. We observe galaxies, stars enter, well, dark matter doesn't directly enter our, obviously, our observations, and stars enter our observations preferentially if those stars are very bright or nearby, and so on and so forth. So the frequency of stars in the data is in no way representative of the frequency of stars in phase space. Okay, so we want to build dynamical models, I models, which, well, in the 1980s, galaxy models lived in real space, I think it's fair to say. People would from photometry try and work out what the density of stars was in X, Y, and Z, as it were. And they would put in some kind of a model for what the density of dark matter was in X, Y, and Z. And they would measure some mean velocity as a function of position on the sky. They would measure some kind of velocity dispersion at each position on the sky. So there was no real discussion of phase space. It was a question, the object, the galaxy was a sort of hydrodynamical object that lived in real space. It is vital to work in phase space, in XV space, for several reasons. One is that dark matter um, is a very important component, and the way it behaves depends on its velocity distribution. But more obviously, we have five-dimensional and six-dimensional data from Gaia. So we have, for this 1.5 billion objects, we have uh, astrometry, we have motion across the sky, and we have some information about the three-dimensional location of the star from parallax uh, and position on the sky. Uh, but we also have six-dimensional data for what's approaching 100 million stars from Gaia, the ones which have RVS spectra. And from MUSE, we get three-dimensional data. That is, say, we get positions on the sky and we get line of sight velocity. So we have information which is neither entirely spatial nor complete six-dimensional phase space information. And I feel that we need to move beyond Jean's equations-based models, which were very much the kind of technology used in the 1960s, when, as I say, galaxies lived in phase space and people felt they knew what they were doing if they knew what the mean velocity was at each point and they knew what the velocity dispersion was at each point. And so a major reason for feeling that Jean's equations-based models are not good enough is that the velocity distributions in galaxies or stellar systems generally are by necessity non-Gaussian. They can never be Gaussian because a Gaussian extends to infinite, has non-zero probability to infinite velocity, whereas every stellar system has a finite escape velocity. But as we know from our own galaxy, the actual velocity distributions are very non-Gaussian. And I think we now know that crucial dynamical information is buried in the velocity distributions. The deviations of velocity distribution from Gaussian are dynamically very important. Galaxies, so there's been a lot of excitement since Gaia DR2 came out by indications that our own galaxy is out of equilibrium. And there's no question whatsoever that it is out of equilibrium. It is not in a statistical steady state, but it is quite near to equilibrium. The deviations from equilibrium are small relative to the whole, and the correct procedure, in my view, is to build equilibrium models and then to focus on discrepancies between the predictions of an equilibrium model and the actual data to point you to interesting deviations from equilibrium, which will be associated with oscillations, disturbances coming from outside, whatever. Building phase-space models is hugely simplified by assuming statistical equilibrium. And that's why, so equilibrium models are much easier um, uh, to determine than going straight to a full non-equilibrium thing. And we can, once you've got an equilibrium model, because we know the deviations from equilibrium are small, we can study disequilibrium by perturbation theory, which is the central, in pretty much every branch of physics, perturbation theory is a central tool. This is what I'm arguing for here in galaxy modeling is simply what we do in pretty much every other area of physics. Okay, so what should we be doing? We should be synthesizing the data into chemo-dynamical models. So each galaxy should have a chemo-dynamical model, which is consistent, ideally, with or with all the available data. I suppose really what we should be pushing for is knowing which of many chemodynamical models, which classes of chemodynamical models are consistent with the data. The models are going to reveal the distribution of dark matter, which effectively you cannot determine the distribution of dark matter beyond the assumption of statistical equilibrium. If you argue that the system is in equilibrium, you can probably get quite close to pinning down the matching dark matter distribution. But if you don't make that assumption, I believe there's nothing much you can say about the distribution of dark matter. And then you will, from these models, are going to reveal internal structures that portray whether the galaxy formed through the quiescent accretion of gas, which I believe is the case in our own galaxy overwhelmingly, or whether there have been major mergers, or whether or track various minor mergers, which we know are pretty common. And then we will perturb these equilibrium models to understand things like spiral arms, the famous Gaia phase spiral in the ZVZ plane, but also we hope to get to the bottom of large-scale distortions, warps. Our own galaxy has a warp disk, uh, center offsets, that is to say, the outer part of the galaxy appearing not to be centered on the inner part of the galaxy, and processes which we know are very important, such as secular heating, that is to say, the slow diffusion of stars through phase space as a result of the small fluctuations in the gravitational potential associated with the small levels of disequilibrium that are endemic. And what is a chemo-dynamical model? I would say that it's an ensemble of orbits with specified numbers of stars, or dark matter particles as appropriate, stars being ordered by age and chemistry on that orbit. So what about an n-body models? Do they solve our problem? Well, the thing is, in an n-body model, an n-body model is effectively specified by the initial conditions. You arrange your particles in phase space with certain initial locations in phase space, certain x's and v's, and then you set them going. And the system settles down to some kind of near equilibrium. And the problem is that in general, there's no clear relationship between your initial conditions, xv sub 0, and the orbit that the final particle settles to. If you start your particles from an equilibrium model, then there is a relationship between xv0 and the orbit of the particle, obviously, because you've started it on the orbit that it's going to settle to. But most n-body modeling is done by starting from initial conditions which do not correspond to an equilibrium model because of because historically we haven't been in a position to create equilibrium models so you start the initial conditions from which n-body models normally start are either not at all nowhere near an equilibrium, as in a cosmological Zoom simulation or whatever, or they're moderately off equilibrium because the thing has been started using some approximation, some scheme using the Jeans equations or whatever for making a near equilibrium model, but it's not an equilibrium model, and the early stages of the evolution are always some kind of minor relaxation. And it's hard to steer the final n-body model onto observational data. There is a very important made-to-measure technique dreamt up by Sire and Tremaine and developed by a number of other people like Gerhardt, Orwin Gerhardt's group. And it's an important method, but it's very laborious, requires a lot of intervention, and is not an ideal solution to the problem. And finally, or not, I would say a serious drawback of n-body models is the structure of the final model is not easy to understand. The model is characterized by on the order of 10 to the 10 numbers. That would be the right number if the model had, say, 10 to the 9 particles, because each particle is associated with on the order of 10 numbers. But all these numbers, or well, most of these 10 to the 10 numbers, are time varying and are individually insignificant. So it's statistics of these numbers which is significant, and extracting those statistics is already a major enterprise, rather similar to understanding the dynamics of our own galaxy, where we have a similar number of numbers on the order of 10 to the 10 numbers, all which are in principle time varying, et cetera, et cetera, et cetera. So the n-body model is not enormously explicative in that sense that once you've got it, you've got an enormous amount of work to dig the physics out of it. And of course, it's extremely hard to communicate. And communication is a very important part of the scientific enterprise. In principle, everything we do ought to be replicated by a colleague or some colleagues somewhere else. That's sort of principle of the 17th century scientific revolution that you what we when we publish, we don't make ex cathedra statements. We don't claim that this is true because we've had divine inspiration or we have superior knowledge. We're making a prediction. We're saying, I've done this and I've seen that and that and measured the other thing. You do it, and you will find the same. I'm predicting you'll get the same results. That's the nature of a scientific publication, and and I think it's a serious problem if it's difficult to communicate. If it's models ought to be, to be most useful, they should be communicable. They should be easy to publish so somebody else can get them running on their computer and play with them. Oh, sorry, wrong thing, wrong thing, wrong thing. Okay, so a chemo-dynamical model is an ensemble of orbits, as I've said before, with numbers of stars with age and chemistry. And so what we need is a scheme. What's central to this is a scheme for labeling orbits, because a chemo-dynamical model is an ensemble of orbits, and we need a way of labeling orbits which is distinctly model independent. I mean, which makes some kind of absolute sense, isn't just arbitrary initial conditions when you could have chosen other initial conditions and got the same model. So let's talk about Schwarzschild modeling. In Schwarzschild modeling, you generate orbits by sampling phase space on some scheme. And you effectively label the orbits with the initial. So, sorry, I should have said before that in Schwarzschild modeling, you hypothesize a gravitational potential up front, right? So you say, we're going to build a model around this gravitational potential. You generate orbits in that gravitational potential, and you effectively label the orbits by the initial conditions from which you start your orbits. These labels are highly non-unique, obviously, because any point along an orbit would generate the same orbit. You can take any point along an orbit as the initial conditions for your integration, and you'll get the same orbit. So that's a problem, the non-uniqueness of the labels. Another issue is that the phase-space density of the sampling is typically not evident. The sampling scheme has to be your sampling. The sampling scheme typically is such that you don't know the the relationship between the density of orbits in your orbit library and the density of orbits in phase space, which is something which is physically significant. So I want to talk now about actions. Obviously, any label of an orbit is by definition a constant of motion, because as you go down the orbit, you're on the same orbit, therefore you have the same label. Any function of a set of constants of motion, I1, I2, I whatever. So if I1, I2, etc. are constants of motion, any function of those constants of motion is clearly also a constant of motion. That means that there's enormous choice. We have tremendous freedom of choice in what constants of motions we use, because any set of constants of motion can be used to derive an infinite number of other sets of constants of motion. But the key point is that very few choices of constants of motion yield constants that can be embedded in a canonical coordinate system. So most constants of motion, and this includes energy, crucially, are not such that you can find that it can be embedded in a coordinate system for phase space. And embeddable constants of motion are what are called actions. And because they're embeddable, they come with canonically conjugate variables, and the canonically conjugate variables are what are called angles. And these some system of embeddable coordinates, actions and angles are the orbit labels we should use. The problem, of course, with angle action variables is the problem of how to compute them. So clearly they're useful only if we can compute the transformation from x and position and momentum, x and p, to angle variable and action, theta and j. And we need to be able to do this in both directions, given x and p, just ordinary easily accessible phase-space coordinates. We want to be able to find what theta and j are, but also given theta and j, we want to be able to find to what point x and p in phase space those labels point. Ultimately, our maps between these pairs of phase space variables always rely on the Hamilton-Jacobi equation, which is the equation you get if you take the trivial statement that the Hamiltonian x and p is equal to the energy of your orbit. So h and saying that x and p, if they lie on a given orbit of energy E, have to satisfy h of x and p is equal to E. This trivial statement becomes the Hamilton-Jacobi equation when you replace p by ds by dx, where s is the generating function of the canonical transformation between x and p and theta and j. I should have said earlier on that this transformation between x and p and theta and j, because it's a transformation between canonically allowed coordinate systems, has to be generated. There has to be a generating function that affects this transformation. There has to be a function s that does the trick. And if we simply say that if we say that p is ds by dx and theta is ds by dj, then we get a partial differential equation, the Hamilton-Jacobi equation for h of x and ds by dx is equal to E. This equation is an approximation to it. It's a classical limit of an equation that we all teach all the undergraduates in their first quantum mechanics course. This is the time-independent Schrödinger equation. It's an iconal approximation to the time-independent Schrödinger equation. So the trouble is that the Hamilton-Jacobi equation can be solved in very few cases. For very few potentials can you solve this thing. Those potentials include the Kepler potential and the harmonic oscillator potential. But we have found over the last 20 or so, 30 years, ways to extend these solutions to realistic potentials. And I'm going to talk a bit about that now. To do the transformation from from theta and j to x and v, that can be done numerically with a torus generator. So Paul McMillan and I in 2016 published a torus generator, and with an undergraduate student, Tom Wright, Eugene Vasilyev and I are about to post a new version, an update of this that is native to the A-gamma, to Eugene Vasilyev's A-gamma software package. A torus generator is essentially, you should think of it as a plug-in replacement for a Runge-Kutta integrator. What you supply as a user is a function that gives the gravitational potential at an arbitrary location and gives the gradient of the gravitational potential at an arbitrary location, just as you would for a Runge-Kutta integrator. Then when you specify an action J, the torus generator returns analytic expressions for x as a function of theta and v as a function of theta. And we call this thing a torus because topologically in six-dimensional phase space, this thing is a three torus. It's a torus because with the action suitably scaled, theta, the angle variables, theta 1, theta 2, and theta 3, the x is 2 pi periodic in each of these components of theta. So this thing has the topology of a torus, of a three torus in six-dimensional phase space. The point that I would like to stress is that a torus is much more than an orbit. So I'm saying there are analogous games you can play here. Given a potential phi of x, you can get your Runge-Kutta integrator or some other integrator, and you can find a time series x of t and v of t. Um, or you could plug these self-same functions into a torus generator, and you would get out x of theta and v of theta, the torus. And the point is that the torus is much more than an orbit. One of the things it can do is it can be used to obtain a time series, because we know that theta is linearly is as a function of time. The angle variables increase linearly at a rate given by the frequencies omega that are computed by the torus generator. So given x of theta, you can replace theta of t by theta of naught, some initial condition, plus omega times t, and you get the orbit. And on the right hand, what you see in the picture on the right here is a fairly eccentric orbit in a NFW like, no, in a Hernquist potential, where plotted in red is the Runge-Kutta into the result of integrating by Runge-Kutta the orbit from some initial condition that you can see sort of at the bottom, quite low down. And in red, sorry, that was in red, and in black, overplotting the red is the time series obtained by solving for the torus and then replacing theta by theta naught plus omega t. So we can, out of the torus, we can get any time series we like. But we can also ask other questions. We can say, it is some point x on the orbit. Just choose any old point x. Will it be visited by that star eventually, possibly after an infinite lapse of time? And if it is visited, with what velocity? Well, the torus will answer that question. It might, if you give an x that lies outside of the the spaces that are visited by the orbit, it will say it's not visited. But if you give a location that lies within, for example, in this picture, we have an orange cross up here, and that's the result of asking the question, does it visit that point? The answer is it does visit that point. And then with what velocities? Well, the orange lines are indicating the velocities with which it will eventually pass through that point. There will be four velocities because it'll come and go along each of those orange things if you wait sufficiently long. It will also tell you what is the density that the orbit will contribute at an arbitrary point x. And in the next slide, we have an example. So here is that same orbit you saw before, plotted in log density. So red is low density, blue is the highest density, green is some other density. So this is a logarithmic scale in density, and of course this is pixelated because I've plotted it on a grid, but the function tells you what density you will get at any point. So it could be done on an even finer grid I mean, the grid can be as fine as you like. There's no inherent pixelization. And you see the characteristic density profile of an orbit that the density is very high. In fact, it's strictly speaking singular around the edge of the orbit and low in the middle of the orbit. So this is what you get from the torus mapper as a function of density. This is what you get if you sample the orbit for 10,000 times, the same orbit, you sample it at 10,000 different times, and you can see that there are places where the places of very low density, even after 10,000 samplings, are not actually visited, and you can see sort of irregularity and so on and so forth. So it's clear that if what you want to compute is the density, as you would, for example, when you're doing Schwarzschild modeling, you're much better off using a torus than using a time series. Another thing that a torus will allow you to do is to draw surfaces of section. So a very valuable way of diagnosing what's happening in dynamics is the technique of Poincaré surfaces of section, where we plot horizontally, for example, a coordinate r and vertically the conjugate momentum vr when we impose the condition, for example, z equals naught. So we every time a star passes through the galactic plane, we note it's the radius and radial velocity or v, radial component of velocity at which it passes that point, and then we get a series of this. These little circles are actual time obtained by integrating the equations of motion, etc., etc., etc. The curves are all drawn. Focus on the black curves. Ignore the green curves. They're all drawn by the torus generator. The torus generator doesn't have any discreteness in saying it knows exactly at any r what the VR is going to be. Okay, so it's an excellent way of drawing surfaces of section, and uh, and I think very crucially, you can interpolate between toruses. You can find by interpolation you can find other toruses. So you can't interpolate between orbits, but you can interpolate between toruses, and this is to illustrate the point that here we have a dotted red curve, which is obtained by linear interpolation between this torus. I should have said, sorry, that each of these curves in a surface of section is effectively a cross section through the torus. So you can think of this as a donut that comes out of the screen, goes round and goes back in on the other side, and this. So this is a rather eccentric orbit. So it's a torus which surrounds this smaller torus, and here is a middle torus. Well, the black curve is what's computed by the torus generator, and the red curve is obtained by linear interpolation between this torus and this torus. So, and it's incredibly cheap to compute, to do linear interpolation between tori. Computing the torus requires a certain amount of work. Linearly interpolating between tori is extremely quick. So that's something that you can do. And because of this, toruses become a platform for perturbation theory. I'll talk a bit about that soon. The inverse map. Okay, so I've talked about torus generators are the map that take you from theta and j to x and v. The inverse map from x and v to theta and j is actually more valuable. It's the map of choice, because when you're doing galaxy modeling and solving for the gravitational potential and that kind of thing, also when you're computing observables, you very much want to do this kind of thing. You want to work out the density, which is the integral over velocities of the distribution function, which is a function of the actions and depends. So this integral over velocities, what we need to do is compute, given x, or given the place we're trying to compute the density, given our current velocity, we want to be able to compute the action j, because that's the argument of the distribution function, and this will give us this. Similarly, if we were going to calculate the mean velocity or the velocity dispersion, we're doing the same integral with a v or a vi, vj additionally added to the integrand. So the way we have to do this at the moment is a thing called the Stekel fudge that I introduced in 2012, and using Vasilev coded in a very efficient way in his A gamma package published in 2019. And this has been enormously used. I'll be showing results later done with the Stekel fudge, but we shouldn't lose sight of the fact that it has serious limitations. It doesn't have a very solid intellectual foundation. It's called a fudge because it arises from assuming that in a general potential, relations hold which actually only hold in the very special potentials Stekel potentials that have separable Hamilton-Jacobi equations. Um, and I'd just like to point out that um, the action finder we hope soon to publish, that is native to A gamma, comes with an action finder which you can which you can use to do this transformation. Oh, sorry, dear, I've gone ahead. That you can use to do this transformation here. It's But the problem with it is it's very much more expensive than the Stekel fudge, and I think we need to explore somewhat um, whether this can be made cost effective. Anyway, right. So for the moment, I think we're rather with the Stekel fudge. Okay, I want to talk briefly about resonances. So real potentials, unlike these idealized ones that I'm talking about, don't admit global angle action variables. And a way to think about a torus generator is it's a device that creates an integrable Hamiltonian, that is to say, H, which depends only on the actions, and by the actions I mean a global set of angle action coordinates, which is very close to the given Hamiltonian. And then, and moreover, the torus generator it creates an integrable Hamiltonian, and then it gives you the difference Hamiltonian h of x and v, your actual Hamiltonian minus the one it's just created, which is small. So this is going to be small, and now we can do perturbation theory using this as the underlying integrable Hamiltonian and this as the perturbation. And I've published a number of papers doing this, both in axisymmetric potentials and in barred potentials, taking the axisymmetric potential as the unperturbed system. Just to give you a flavor of this, so here we have this is a surface of section of a realistic galactic potential for stars that move around the sun. So the sun, of course, sits here at about 8 and a bit kiloparsecs at quite a small, so it sits here in some sense, at quite a small radial velocity. And what you see, the dots are, this is a classical surface of section obtained by integrating the equations of motion and et cetera, et cetera, et cetera. So there's nothing about torus generation here. This is just classical Runge-Kutta integration. And by there not being a global system of canonical coordinates, what that means is that there's this blue island here. So in the classical picture, if there were global angle action coordinates, we would see a series of egg-shaped objects that went all the way from the outside, from the most eccentric orbit, all the way to the inside, which is a sort of shell orbit, an inclined circular orbit, as it were, completely smoothly and nestedly. But we don't have that. We have here an empty space, and here we have a series of moon-shaped curves which center on this. And this is the one-to-one resonance. I mean, this island is arising because of resonant trapping between the vertical motion and the horizontal motion, the radial motion in the given potential, because it's a real potential. It is not a separable potential. It's not an integrable Hamiltonian. So how we can handle this? So this diagram is illustrating how effectively torus generation solves this problem. So these greeny colors, these greeny curves are are they're cross sections through toruses of the integrable Hamiltonian h of j that the torus generator has constructed. So it is constructed, it is forced through this region a large and in principle an infinite number of uh, of green curves. And then it is also returned the difference between the real Hamiltonian and the Hamiltonian which is constant on these green curves. And then with perturbation theory, so analytical uh, solution of the Hamilton's equations in theta j space, it has drawn these curves um, in red, uh, which are the orbit as predicted by the perturbation theory using the separable potential which it is constructed with the green curves and the perturbing bit that it's computed from the real Hamiltonian minus that one. And so those are the pink curves, and the blue dots are these blue dots from over here, obtained by Runge-Kutta integration. And you can see that the perturbation theory is absolutely perfectly, astonishingly degree of perfection. It is, given that it's only first order resonant perturbation theory, it is reproducing the Runge-Kutta thing. So torus generation is capable of handling resonantly trapped orbits, and by creating, you should think of it as a tool which creates an integrable Hamiltonian, which is what you need in order to do perturbation theory. And it does, the perturbation theory works amazingly well because it creates an H of J, which is so close to the actual potential that the perturbation theory works. In classic, when you do classical perturbation theory, um, uh, the problem typically is that you're using for H of J um, uh, a, a Hamiltonian which is emerged by solving the Hamilton-Jacobi equation. So it's a harmonic oscillator, it's a Kepler or something, and that isn't sufficiently close to the actual Hamiltonian. Here we're tailor-making an integrable Hamiltonian that isn't, which we don't get by solving the Hamilton-Jacobi equation, and we are able to make one that's very close. This is showing the interesting. This diagram is showing the interesting astronomy associated with this one-to-one resonance. So this is, again, we're seeing in pink the we're seeing in pink the resonantly constructed torus. So that's one of these curves. I can't remember which one. And in blue, we are seeing the Runge-Kutta integration. And the point is that these stars, these resonantly trapped stars, circulate in the RZ plane. So this is distance from the galactic plane. This is radius. The sun is sitting here, and these stars are dancing around the sun in the RZ plane, and it would be it. So it offers the possibility, it's not a necessity, but it could be that on one side of the sun, there is a net upflow of stars. These will be stars they're stars with large vertical excitations, right? They're going to 2 kiloparsecs or more, and more above and below the plane. So these are what you would call thick disk stars. But there's a possibility that on one side of the sun, there's a net updraft, and on the other side, there's a matching downdraft because stars are going around like this. The trouble, of course, is that there are equal numbers of stars that go around this way, clockwise and anti-clockwise, and it's likely, I mean, unless we're lucky, the number of stars going one way is balanced, is equal to the number of stars going the other way, which means that we can't actually detect a net updraft here and a net downdraft there or whatever. But that logical possibility exists, and I think Wynne Evans told me he'd look for that in the Gaia data and not found it, but you never know. Okay, so let's get back to the data. Dear, time has gone on rather, hasn't it? Back to the data. Apogee and H-band spectroscopy, the apogee data, which comes from H-band spectroscopy, so it penetrates a lot of the dust in the galactic plane. It provides the most amazing, combined with Gaia DR3, the most wonderful probe of our own galaxy. So these are diagrams showing the distribution of stars in the survey in the XY plane. So the sun sits precisely here at the middle of this star. The galactic center is just off the picture here. We have this enormously heliocentric image of the galaxy, um, because the observations are taken by picking fields on the sky, etc., 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 largely avoiding lines of sight towards the galactic center because of the desire to avoid dust. And this is showing the ZX projection of the stellar distribution. Um, so again, we have this enormously heliocentric. So this is the problem. This is one of the problems that we have to address with observations of our own galaxy. This enormously strong bias towards towards the sun. So that was just pure observations in the previous picture. Here we've used the Stekel fudge to compute the JZ, the action of vertical motion um, uh, for those stars. And you see the great clustering of stars near the sun. The sun sits down here at low JZ and about 2,000 kiloparsecs kilometers a second. So this blue color of high density of stars is simply because these stars are on orbits close to the solar orbit and so feature largely. The thing that's really striking for me about this diagram is this cliff edge. I've lost my thing. This here. So just beyond J phi equals naught, so just where, so stars on the left side in principle here are rotating around the galaxy anti-clockwise, the opposite way that the sun is, and on this side they're rotating clockwise. This very sharp edge here, which I think is indicative of a complete cliff edge at J phi equals naught, which has been smeared by observational error. Why observational error is important is this lower panel is showing stars with relatively small radial actions. So these are not stars on deeply plunging orbits. By definition, they have JR less than 60, no, 50 kilometers, kiloparsecs kilometers a second. So the stars that represent these points, that are contributing these points here, are stars which do not come close to the sun. They are actually observed deep towards the galactic center. And so small errors in their distances will be significantly uncertain, and errors in their distance can easily push them across this line into having negative angular momentum. So this diagram is an indication that the disk of the galaxy, that the overwhelming majority of the stars in this survey, and indeed in the galaxy, formed in the galaxy, in the disk, rotating the same way that the sun does. And this is showing the same kind of the same thing, but for stars which are on highly eccentric orbits. And you can still see that there's a significant drop off in this zone here. Okay, so so Eugene Vasiliev and I modeled this data set by choosing distribution functions for disks. We had 4 disks, 3 components of the thin disk, the low alpha disk that we thought of as belonging to disks of different ages, and a high alpha disk. We had a distribution function for the bulge, a distribution function for the stellar halo, and a distribution function for the dark matter. These distribution functions all depended on parameters. These parameters were adjusted. And then we solved for given distribution functions, we can then solve for the gravitational potential. And we looked for a gravitational potential which gave a decent fit to the kinematics at many different spatial locations. We did it that way because the data, as I've shown, are incredibly biased by location, by physical position, but they are not biased by velocity. So the velocity distribution at any location is a reflection of the intrinsic velocity distribution, is not affected by observational bias. And then we found distribution functions which generated a potential which generated a good fit to the kinematics. And then we examined the chemistry in the 5-dimensional space of alpha over Fe, Fe over H, and 3 dimensions of action space. So the stars, each star has 3 actions and two chemical late tags. And we represented the distribution functions by saying, so the distribution functions, extended distribution functions depend on the actions and on the chemistry, but we chose to write that as a purely dynamical distribution function times a probability of having chemistry J given, chemistry C given actions J. And this thing we took to be a Gaussian. So at any given J, this was a Gaussian, and the dependence of the mean and the dispersion of the Gaussian on J was assumed to be linear. So this was a very minimal kind of model, uh, um, where we were attempting to capture what we see here, which is so the color here, and this left side is plotting magnesium over iron. So this is high alpha, and this is low alpha, and this is stacked. Up here, we're increasing, we're looking at increasing bands of JZ. So down the bottom, we're talking about stars which have small JZ. Actually, on the left here, this is JZ, um, and we're stacking them by JR. So these are stars on rather circular or not very eccentric orbits. And down here, they have also low JZ. So this orange structure here is the thin disk, and it is low alpha as you see because it's kind of orange in color. And this structure here is the high alpha disk, the thick, sometimes known as the thick disk. This is the bulgy kind of thing. And you can see that when you go to highly eccentric orbits, the low alpha structure kind of just plain disappears, but the high alpha structure is still present at low JZ. It's not right. So there are orbits. Some of the high alpha structure of the thick disk is on orbits which keep them so they stay within the galactic plane. They don't all go to high altitude, et cetera, et cetera, et cetera. So there's an enormous amount of information in these kind of plots. Over here, we're seeing the same thing in Fe over H. The thing which I think I should be stressing here is that this high alpha structure, which is blue, just dies. It's cut off, just really sliced off with enormous sharpness at the angular momentum of the sun. And I think this is an enormous mystery. So there is a thick disk at higher angular momentum than that of the sun, right? These stars here, but it's a low alpha structure, not a high alpha structure, whereas at lower angular momentum, it's a high alpha. That's the most striking thing for me in these diagrams. We had a go. So this is again just pure observation, apart from the Steggel fudge. In these pictures, I'm showing what I consider to be an unsatisfactory, I mean, a not sufficiently successful attempt to understand the structure in the five-dimensional space that I just spoke of. So what we're doing here is we're taking the J phi JZ plane. So this is essentially radius along here, right? The sun's sitting here, we're moving outwards, and vertical excitation plotted this way. And we're colored by the velocity dispersion in mg over Fe, so the homogeneity. So don't worry about it. But here it's very inhomogeneous. Here it's very homogeneous. Whatever. We've divided this space, this angular momentum space, or its action space, into four areas: A, B, C along the bottom here, and D being bulgish, high alpha, thick disk, whatever. Down the bottom here, low alpha, thin disk, and this is the outer disk, the flaring outer disk. And then what we're plotting here, the colors are showing mg over Fe in each of these areas. So in area A, bulgy area, we get this kind of distribution. So this is this is the chemical plane Fe over H versus mg over Fe. So high alpha structure, low alpha, high metallicity out here, right? So this is what you would expect to find broadly in the bulge region. This is showing the this B region, which you would associate with the high alpha disk, and indeed here is a big island of high alpha, um, and it's colored. The colors, sorry, this is J phi, this is JZ, and this is JR, showing the colors. This is the thin disk. This is the bottom region, stars with very low JZ. And it's colored by J phi, JZ. And the most interesting thing here, I guess, well, the coloring is telling you about the metallicity gradient within the because J phi is obviously very strongly associated with radius, and so this drift of colors from red, which is low angular momentum, therefore small radius, to high angular momentum is a radial drift. And down the bottom, we're seeing the structure of the region D, which uh, um, it's remarkably richly structured, right? Um, um, uh, so anyway, what I what I want to say is I think this is an attempt, I think not a very satisfactory attempt, to get a grip on the structure of the galaxy in this five-dimensional space. The way we've sliced this up is probably suboptimal. Um, how you should, yeah. Let me talk, therefore, about a completely different approach, Kopasov et al. To what they did. Their work differs from ours in a number of important respects. First, they fixed the gravitational potential. They didn't solve for it. They fixed it from Samani et al. 2022, and moreover, they used a barred potential, as of course they should do. We used an axisymmetric approximation to the potential. Then they integrated the orbits Runge-Kutta-wise for each of the apogee stars. So they said each of these apogee stars has a present phase-space location. Let's just integrate the orbit from that location for 5 gigayears. And then they stored 100 um, uh, locations per gigayear. So they had 500 locations, phase-space locations for each and every one of the apogee stars stored away. And then they sought weights for these orbits such that the density contributed by the orbit, and obviously over 5 gigayears, a star which is currently near the sun and has been observed because it's near the sun, uh, has time to cruise around the galaxy and spread itself around in a fairly uniform way. So it's reasonable to say that if we take a weighted sum of the densities contributed by all the different stars in the apogee survey, they should give you the density that generates this with some hypothesis about dark matter, some reasonable hypothesis about dark matter, and they're doing this regardless of chemistry. And so this is the data. So again, you're seeing the line. So this is X and Y. I've shown you basically this picture uh, in a different representation before. Well, except I showed you the number of stars as a function in X and Y from just the raw data from the survey. Here they're colored instead of by number, they're colored by radial velocity, v phi and vz, the three components of velocity. And down the bottom is here is their model that they obtain by taking this. So by taking this linear combination of the actual apogee orbits, they get this model. And then when they observe this model the way that Apogee observed the real galaxy, they have the pseudo data down the bottom, and they're obviously doing fairly well, not perfectly, but fairly well reproducing uh, the data. That is all chemistry independent. Uh, and now they're trying to understand their model. Here we are seeing two-dimensional projections of these. They've got now a kinematical model, a dynamical model. It's in six-dimensional phase space, and here are a number of two-dimensional projections of six-dimensional phase space. So looking at this picture, I think is analogous to looking at an engineering drawing. I see this as analogous to looking at an engineering drawing um, of a three-dimensional object, right? An engine or something. Anybody who's ever done any engineering knows this is a skilled, difficult thing to do to specify a three-dimensional object and you with two-dimensional projections, and it's something which, of course, you have to learn to do if you're a student of engineering. Here we have an immensely harder job because we're looking at a six-dimensional object and we're trying to understand it through its two-dimensional projections. And I personally don't feel equal to this task. Um, and so here are some other diagrams from Kopasov et al. Um, here is the chemical plane plotted colored by the mean by R guiding. Now, R guide the guiding sensing radius, so that's a proxy for angular momentum J phi. This is this is colored by the minimum the radius. So pericentric, if you like, radius. Here's the apocentric radius. Here is eccentricity. These are all sort of numbers associated with orbits. They're sort of labels of orbits, but they don't have the coherence of actions or the uniqueness of actions. These are just a number of, so Rmin and Rmax together with this will specify JR, the radial action. And this R guide effectively specifies J phi. Z max is some sort of proxy for JZ. Mean eccentricity, well, that is something which comes out of these. So my point is that these are labels, orbit labels, but I don't think they're very good orbit labels. They also use plot stuff. This is Fe over H plotted against circularity. So uh, um, gosh, I've forgotten the exact definition of that, but it obviously circularity of one is stars which are on orbits like the sun, which are circular orbits going around the same way as the sun. Orbits with circularity -1 are going around the opposite way on circular orbits, etc., etc. And as you go down here, they're getting more eccentric. And then they've broken it by different radiuses. So these are attempts to understand their six-dimensional model. Now, the previous picture was just understanding the six-dimensional model. Now we're understanding the six-dimensional model with chemistry put in, so it's become an eight-dimensional model because we've got two other things. Oh no, more than that, it's become a nine-dimensional model because down here we have what Vasilev and I didn't have, which is the age data. And so we can see things like, no, well, there are things you can see in these diagrams, but it's very hard work. I think it's time I wound up. It's definitely time I wound up, isn't it? So my conclusions, equilibrium dynamical models are the key to extracting science from current data. Galaxies are ensembles of orbits, and a model should specify orbits are populated by chemistry and age. Orbit labels, because of this, are of fundamental importance for this enterprise, and action integrals are uniquely favored labels, and we can now compute them, although I think computing them is a technology that still needs to be pushed. The cleanest description of a galaxy is a stellar distribution in action space by chemistry and age. So this would be a six-dimensional distribution, and it's very challenging to understand such a six-dimensional distribution. I've described two attempts to model our galaxy, and I think neither is entirely satisfactory. We need to regroup and make fresh attack on this problem because I think it's a fundamental problem. And substantially, it's a problem of visualization or maybe of characterizing a structure that lives in a space of fairly high dimension, which is difficult for us to imagine. Yeah, I think that's pretty much all. And thank you for your attention. Sorry, I think I've gone over time rather.
Excellent, James. Thank you very much for this fantastic overview on modeling our Milky Way and also the challenges we are facing with. We are late in the game, but I hope we still have some time for some questions. So the way to do it would raise your hand in the Zoom feature because it orders it by time. I don't see any so far.
Maybe I
What
can
was? Yeah, go ahead.
ask questions for the Hopperscroft. For the Hopperscroft page. Yeah, you showed
Yep.
mechanism
You,
and
you'd like to see a Kopperswolf, right? Okay.
the page. Maybe I think the 20. I think so. The 20th page, I guess. Yeah.
Oh, 20.
Slide 20. Yep.
Oh, okay. That's not Kopperswolf. That's
Oh,
yes, right. That's
sorry.
us.
Oh, maybe 22. 22. Sorry, 22.
22.
Yeah, it's
Yep.
the model 22. The model we can see we can see here the model patterns, the blue and red patterns. This shows the X shape of the bulge, isn't it? Easy. I'm not sure.
Yes, I think, well, Matthias is probably the right expert, but I think you can see I mean, you can see the bar, right?
The bar,
Yeah.
I see the bar, but I'm not sure it is a
It's
X.
showing this quadrupolar structure in velocity space because of the.
I mean that's the beauty of this apogee work. So basically, what it is it uses apogee and Gaia, and then put that in a coherent model and use it also information also to improve the distances, and that way we're getting a cleaner signal on the quadrupole moment of the bulge and on the bar, and you very nicely see the bar in velocity space here.
Okay. Yeah. Okay. I noticed the question in the chat.
So there's a question in the chat that real galaxies have dynamic components beyond stars, such as dust, gas, and so on, which are mapped by other surveys. And
Yeah,
these
right.
components are also part of the contribution to the potential. So to fully understand the dynamical nature of the galaxy, we should account for these two.
Absolutely. Yeah. And of course, it's a central issue about Gaia analysis is that that even in apogee, dust has a big impact on Gaia because it's in the optical, and even in apogee it has an impact, right? Not so we need to map in order to clean out or to get rid of the observational biases, we have to deal with the dust issue. But anyway, I believe it provides well, I think we all know that it provides the a vital tool for determining what the dust distribution is. The thing that there's just absolute pain about dust, right, is that it has extremely high frequency structure in real space. So, it's an almost fractal thing, the interstellar medium, and so in order to map it, you've got to have a very dense collection of objects that you have to probe it very densely in real space. And Gaia offers the opportunity to do that. It's completely unparalleled because it has this 1.5 billion stars, whatever. And I believe strongly that the way we should be doing this, but we're not doing it, is we should be building these. One of the things we need to do with these dynamical models, both of these studies illustrate this point that that a dynamical model allows us to predict how many stars there are everywhere in the galaxy with great certainty. I think our potentials, we haven't got this matter, what the dark matter distribution is, everything properly pinned down as well as we could, but we know enough about the galactic potential that we can predict the density of stars from the stars we do observe. We can predict the existence of stars which are hidden from us by dust. And so the way to go, I think, is to compare the number of stars that Gaia sees in some field as a function of distance with the number of stars that we know are there from our dynamical model.
Yeah.
That is going to tell us the dust density with a spatial resolution which is quite different from if we would restrict ourselves to the classical methods based on stars for which we feel we know the spectrum and can infer a reliable extinction. Moreover, it will tell us because there are places where we will see no stars, right? Where you can't measure the extinction if you haven't got any stars. But we will know that there are stars behind there, and therefore there is this dirty great cloud of soot in the way.
I mean, the other thing is that with the subsequent Gaia data releases, I mean, in Gaia DS3, we only had the first look at the spectral information from the RVS.
Yes.
And it's only in a very integrated fashion. And future Gaia data releases will start to disentangle that part of the domain space. So that will also add considerably new information regarding the dust component.
Yeah. But this is an enormous mapping the dust is an enormous task that I think is going to take decades probably because of this problem of the high spatial structure, its filamentary nature, and it's a huge computing challenge to exploit all the information that we have and are getting. And spectroscopy is going to be part of it, but I think just star counts is going to be part of it. Actually, how do you synthesize it? What is the correct way to build a dust model, right? So, which has the minimum number of parameters that is absolutely necessary in order to represent this very complex structure.
Okay, we are well after noon already. I also see the first people are dropping off. So let's take the opportunity again to thank James for a fantastic up-to-date insight into dynamical modeling our galaxy and what is possible in this new era of large data sets. Thank you very much, James, for joining us.
Well, thank you
for your insights.
And
everyone, also thank you for joining, and see you in a month's time, a bit more than a month, in September, when we have Anthony Brown on Gaia data. Okay.
Bye.
Good.
Yeah, thank you.
Thank you.
Hi, James.
Yeah, bye. You can leave first. I forgot the recording for this page, so I use 1 minute to put here, and for anybody interested, this is the first page, and this is the second page for IAU, and this is the third page, and this is the fourth page. Yeah, anybody interested to our IAU seminar, you can submit the form or contact me directly, and see you in September. I will post the video and perhaps the James Binney's PDF of the presentation on the website. Yeah, see you this time. I stop. Bye.